Hi everyone, welcome back. In this video, we will discuss the top JVM interview questions and answers. Let's begin. What is the Java Virtual Machine, JVM, and why is it important? The JVM is a virtual runtime environment that allows Java programs to run on any platform without modification. It executes Java bytecode, not source code, which means the same compiled class file can run on Windows, Linux, Mac OS, or any system that has a compatible JVM. This is the foundation of Java's write once, run anywhere principle. The JVM performs several key functions. It loads class files, verifies their correctness, allocates memory, manages the call stack, executes bytecode instructions, and provides a managed runtime environment with garbage collection. It also isolates and protects the host system by running code inside a secure sandbox. Modern JVMs include JIT compilation and advanced optimization techniques, making Java applications fast and efficient. Because of the JVM, Java supports dynamic loading, runtime profiling, memory management, and performance tuning. In large-scale enterprise systems, the JVM is a critical component for reliability, portability, and performance. Next, what is the JVM architecture? JVM architecture consists of three major components: the class loader subsystem, the runtime data areas, and the execution engine. The class loader is responsible for loading, linking, and verifying class files. It ensures that the code is valid and secure before execution. The runtime data areas include the method area, heap, stack, PC register, and native method stack. The heap stores objects and is shared across all threads, while the stack is private to each thread and holds method frames. The method area stores class-level metadata such as fields, methods, and bytecode. The execution engine interprets bytecode or uses the just-in-time JIT compiler to convert frequently executed code into native machine instructions for faster execution. The garbage collector is also part of the runtime environment, continuously reclaiming memory from unused objects. This architecture enables the JVM to provide security, portability, performance optimization, and automatic memory management. Next question: what is the difference between JDK, JRE, and JVM? The JVM is the virtual machine responsible for executing Java bytecode. It provides essential features such as memory management, security, and bytecode execution. By itself, the JVM cannot compile or develop programs. It only runs them. The JRE or Java Runtime Environment includes the JVM and a set of libraries required to run Java applications. If your goal is only to execute Java programs, installing the JRE is sufficient. It contains runtime libraries, Java class files, and supporting components, but does not include development tools. The JDK or Java Development Kit is a complete toolkit for Java development. It includes the JRE plus development tools such as the Java compiler, JAVEC, debugger, archiver, documentation generator, and other utilities. Developers use the JDK to write, compile, and debug Java code. In short, JVM runs Java programs, JRE provides the runtime environment, and JDK provides everything needed to build Java applications. Next, what is the JVM class loader and how does it work? The JVM class loader is responsible for loading Java classes into memory at runtime. It follows a three-step process: loading, linking, and initialization. Loading retrieves class bytecode from the file system or network. Linking verifies class correctness, allocates memory, and prepares static variables. Initialization assigns values to static variables and executes static blocks. Java uses a hierarchical delegation model with three built-in class loaders. The bootstrap loader loads core Java classes from the JDK. The extension loader loads classes from the extension directories. The application loader loads classes from the class path. Class loaders isolate classes, support dynamic loading, and enable custom class loading for frameworks like Spring, Hibernate, and application servers. Understanding how class loaders work is crucial for debugging class not found exception, no class def found error, and class path conflicts. The class loader system makes Java modular, flexible, and secure. Next, what is the JVM garbage collector and how does it work? The garbage collector automatically manages memory by identifying objects that are no longer reachable and reclaiming their space. This relieves developers from manual memory management and reduces memory leaks. The GC works by tracking object references. Once an object becomes unreachable from any thread or static reference, the GC marks it for removal. Modern JVM use generational GC, dividing the heap into young and old generations. Most new objects are created in the young generation and collected quickly during minor GCs. Long-living objects move to the old generation and are collected during major GCs. Java offers multiple GC algorithms such as serial GC, parallel GC, CMS, G1 GC, and ZGC. Each is optimized for different workloads and latency requirements. Garbage collection improves stability but can also impact performance if not tuned correctly, especially in high throughput applications. Next, what is the JIT compiler and how does it improve JVM performance? The just-in-time compiler or JIT compiler is a key component inside the JVM that improves application performance by converting frequently executed bytecode into native machine code at runtime. When Java code is first executed, it is interpreted line by line, which is slower. The JIT compiler monitors which methods and loops are executed repeatedly, identifies them as hotspots, and compiles them into highly optimized machine code. Once compiled, the optimized native code is stored and reused whenever that method runs again. This dramatically reduces execution time because machine code runs directly on the CPU without interpretation. The JVM uses profiling to decide when to trigger JIT compilation, ensuring that only performance-critical code is optimized. The JIT compiler also performs advanced optimizations such as inlining, loop unrolling, escape analysis, dead code elimination, and constant propagation. These optimizations are based on real runtime behavior, making JIT compiled code sometimes faster than statically compiled languages. In summary, the JIT compiler is what makes Java both portable and high performance. It turns bytecode into highly efficient machine code on the fly, ensuring that long-running Java apps become faster as they continue to execute. Next, what are JRE runtime data areas? JVM runtime data areas are memory regions that the JVM uses while executing a program. Each region has a specific purpose and lifecycle. The method area stores class-level information such as field definitions, method structures, constant pool, and bytecode. This area is shared across all threads. Next is the heap, the largest area which stores all objects and arrays. The garbage collector manages the heap automatically, removing objects that are no longer reachable. Each thread gets its own stack, which contains frames. A frame holds local variables, method parameters, return values, and partial results. Because stacks are thread-specific, they help prevent data races and ensure thread isolation. The program counter register holds the address of the current instruction being executed for each thread. Finally, the native method stack stores information needed to execute native code written in C or C++. These runtime data areas together allow the JVM to manage memory, ensure isolation between threads, and execute Java bytecode efficiently. Understanding these areas is essential when diagnosing stack overflows, heap memory issues, and garbage collection performance problems. Next, what is a Java class file and how does the JVM interpret it? A Java class file is the compiled bytecode produced when the Java compiler processes a .java source file. Instead of platform-specific machine code, the class file contains platform-independent bytecode instructions that the JVM can interpret or compile using JIT. The class file follows a strict binary format defined by the JVM specification. It contains a magic number to identify the file type, version information, the constant pool, access modifiers, method definitions, field definitions, attributes, and bytecode instructions. Because of this standardized structure, the JVM can load and execute class files across any operating system. When the JVM receives a class file, the class loader loads it into memory, verifies it to ensure there is no illegal bytecode, allocates memory for static variables, and prepares the runtime information. After verification, the execution engine interprets the bytecode or hands it to the JIT compiler for optimization. This process ensures safety, portability, and efficiency, allowing Java programs to run consistently across different platforms. Next question. What is the difference between stack memory and heap memory in the JVM? Stack memory is used for storing method frames, local variables, and intermediate computations. Each thread has its own standalone stack, making stack memory thread safe. Whenever a method is called, a new frame is pushed onto the thread's stack, and when the method returns, the frame is immediately removed. Because stack memory is small and very fast, operations on the stack are extremely efficient. Heap memory, on the other hand, is shared across all threads and is used to store objects, arrays, and instance variables. Memory in the heap is not freed automatically when a method ends. Instead, it is managed by the garbage collector. The heap is divided into young and old generations to optimize GC performance. Stack memory is ideal for temporary variables and method execution flow, while the heap is suited for dynamic objects with an unpredictable lifecycle. Most performance issues in Java applications, such as out-of-memory error or GC pauses, relate to the heap. Stack issues usually appear as stack overflow, error due to deep recursion. Next, what is class loader delegation model? The class loader delegation model ensures that class loading happens in a secure and predictable manner. When a class needs to be loaded, the request is first delegated to the parent class loader instead of loading the class directly. This prevents duplicate copies of core classes and avoids security issues. The bootstrap class loader is at the top and loads JDK core classes like java.lang. If it cannot find a class, the request is passed to the extension class loader, which loads classes from the JDK extension directories. If still not found, the request goes to the application class loader, which loads classes from the application class path. If the parent class loader cannot load the class, then the current class loader attempts to load it. This hierarchical approach prevents overriding essential JDK classes and maintains consistency across the JVM environment. Frameworks such as Spring Boot and application servers rely heavily on custom class loaders, so understanding the delegation model helps debug class path conflicts and class not found exception issues.